So before we get into any particular machine learning models, I first want to go over some matrix algebra, matrix math, because it's pretty fundamental and pretty essential for all the machine learning mathematics we're going to be doing going forward. And you may be asking yourself, first of all, what's a matrix? And second of all, why do I need to know what it is? So to answer that first question, a matrix is essentially a grid of values. We draw it like this, and let's say this is the matrix A, and it'll have some values. I'll just fill in arbitrary numbers for now, so like 1, 2, 3. So this is a matrix. It's essentially a two-dimensional array for those of you who know coding or have taken some kind of coding class. Or so like one way you might represent it in code would be like 1, 2, comma, 3, 4. So this is a list containing two elements where each list has two elements in it. So this is our list. It has two elements, this row here, and then within each row there's two elements. And as I say row, I should have specified that the rows are the data, the rows going sideways, the data chunks going sideways, and the columns are the vertical sections of the data. So this would be C1, C2, column 1, column 2, R1, R2. So that is what a matrix is, and that's how we usually draw them. So now what we'll go into is just how can we do different operations on matrices. What are the different operations we can do? So the first one and the simplest one, in my opinion, the simplest one that's not too simple, is called matrix multiplication. And to explain that one, I'm actually first going to start with something you may be familiar with, that being the vector dot product. So let's say you have some vector v1, which is equal to, or let's call it v for simplicity, is equal to v1, v2. So it's some vector and it has two elements in it. And then you have some other vector called u, which has u1, u2. All right. So one operation you may be familiar with between these two is called the dot product. So v dot u is equal to v1 u1 plus v2 u2. And you'll see out of this, what you started with is two vectors, and what you ended up getting out is what's called a scalar. So scalar just means a number. So these are vectors, a scalar is just a number. So using this, we can actually build up what matrix multiplication looks like. So let's say we have, also you'll notice that for here, we drew the vectors, or I drew the vectors in the same notation as I drew this matrix. Actually, because vectors are kind of just a special case of matrices where you only have one row or one column. So that's something we'll cover going forward. So let's say you have some matrix A, and then we'll just give it some simple values. So 1, 2, 3, 4. Maybe I'll draw the next one a little bigger. Then you have B. And let's just do 0, 1, 3, 2. Just put a negative 2 in there, why not? Okay, so the way that matrix multiplication works is we're essentially, actually let's do this. Let's group these up by rows and columns. So this is the first row, so R1 is the second row. R2. This is, and then we're going to group the columns of B, C1, C2. So to do matrix multiplication, we actually use the vector dot product. So we write it out just like, so the way you just represent it would just be A, B, and this is going to equal, so we're going to take the first column of B, the first row of A, and do the dot product between them, and put that in position 1, 1 in the matrix AB. So like in this matrix we have, I guess we'll just use I to denote like a random element. So I 1, 1, I 1, 2, I 1 or 2, 1, I 2, 2. And you'll notice that to get the first element, so to get I 1, 1, we use R1 and C1. To get I think I switched up the ones and the twos. 1 second. So we'll actually do 2, 1, and then, 2, 1, and then 1, 2. So to get this element here, we use the second row of A and the first column of B. So you see that this subscript notation actually denotes which row and which column from A and B respectively you're going to be using. So if we actually do this out, what we're going to get is so 1 times 0 plus 2 times 3, so 1 times 0 is 0, 2 times 3 is 6, so we get 6 for the I11 spot. And then for I12, we're going to take the first row of A and the second column of B, we take their dot product, so 1 times 1 is 1, 2 times negative 2 is negative 4, so negative 4 plus 1, I'm using this equation here, this right here by the way, which is going to be equal to negative 3. I guess for this next one I'll write it out, just to make it explicit. So now we're going to take the second column, or the second row, and the first column, and we're going to do the dot product of those together. So 3 times 0 plus 3 times 4, that's obviously just going to be 12. And then for this last element, we're going to take second row, second column, so 1 times 3 is 3, negative 2 times 4, there's negative 8, so then we're just going to get negative 5. So this is our matrix, and I know I wrote that out, but I'll erase it now just so it looks a little less confusing. So this is how we do our matrix multiplication. It's a fairly straightforward operation. You just need to kind of, the way I visualize it in my head is actually go like this, and then flip these over on top of here, and then flip it over on top of the second one. And then, so obviously right here we did it for the specific case of two by two matrices. 2 by 2 meaning that it has, so A is 2x2, so this denotes number of rows, this denotes number of columns. So what happens if they're not the same size, specifically if they're not both 2 by 2? So what you'll notice here is that we take this C1 and we have to multiply it by R1. And so vector multiplication, so if you have a vector like this, 1, 2, 3, another vector like this, 1, 2, this operation is actually not defined. Because, well, we can do 1 times 1, we can do 2 times 2, but there's nothing to multiply this 3 by. You can't just put a 0 there. The thing to multiply 3 by just doesn't exist. Meaning this is not defined. Not defined. Or I want to do, I forgot the specific math notation. D and does not exist. So because of that, what you can abstract from that into this is that the amount of elements in the columns of B has to be equal to the amount of elements in the rows of A. So because of that, when we do A, B, okay, I'll use my blue from now on, that implies, so if we have A, B, and we have A is n by m, so it has n rows and m columns. That implies that B is m by, I don't know, P. So like this just says the amount of columns that A has, so the amount of columns meaning the amount of elements in each row, has to be equal to the amount of rows in B, otherwise the amount of elements in each column. And then you'll notice here that this N and this P are just kind of left sitting. They can be anything as long as these M's are equivalent. So that's crucial. So A is 2 by 10 implies that B is 10 times P, where P can be anything. But then the question becomes, so what is AB? So what are the dimensions of AB? So the answer to this, just to give you the answer for the sake of time, is that AB is going to be, in this case, okay, let's make this arbitrary. N. So AB is going to be N cross P. So it's going to be N by P. So it's going to have as many rows as A, but as many columns as B. And this is a universal thing. I'm sure I could prove it using math, but that would not be in our best interest for time. So this is matrix multiplication. It's super important, and it's a fundamental operation for machine learning going forward. So did I answer why? Okay, so to answer why this is important, we need to look at the data that we're using. So, for example, let's say our data is someone's height and their weight. So we have height, we have weight, and then we have person. So this is just the person. We'll just number the people, as inhumane as that is. So this is our data set, and let's just say we want to predict their age. So person, height, weight, age. So I don't really know what's reasonable here. Let's just say 5, 9. Wow, that is terrible. I apologize. That's supposed to be a 5 and a 9. So let's say you have 5, 9. So then their weight is, let's say, 160. Their age is 25. And this will all continue down here. So instead of using this weird chart type thing, what we can instead do is we can translate this into a matrix that looks like this. So we can use 5, 9, 160, and then 25, and then we can just keep doing all of our data points. And this is just a more compact way to represent our data than with this kind of chart. And it also allows us to do these fancy operations like matrix multiplication. So right now my board is completely covered in stuff. So I think I'm going to end this video here, and then the next video I'll go over matrix transpose and matrix inverse.